Thanks for the invitation. So this is a noisy robot the kids have been playing with over here. And so you know what I'm talking about, and I think it's pretty impressive what they built. I'm not sure what it's supposed to do, but I guess they have something in mind. And maybe if they spend enough time building and programming, they would actually make it do something really useful. So let me start by telling where I'm from. So I'm from the Technical University of Denmark, which is near Copenhagen, and I'm at something called Center for Playware. So at Center for Playware we combine different concepts like modularity. Like we know from the Lego company, we have a long history of collaborating with the Lego company. So modularity with interaction design, embodied artificial intelligence, the kind of things that we have been hearing a lot in talks today. With robotics, which we have also been hearing a lot about. So we are combining these in different ways in order to create artifacts or devices that motivate people or users to do something they otherwise wouldn't do. So we have examples from rehabilitation, for example, where we build devices which are supposed to help people who suffer from injuries or accidents to be rehabilitated through play and interaction with these kinds of devices. One very active project is about these kinds of jumping tiles, where we are using them to prevent fall accidents in elderly. So they are jumping around, playing games on tiles, and kind of pushing themselves beyond the borders of their balance in order to train and help them increase their balance, so that they don't have so many fall accidents, which are extremely costly, both in terms of money and also in terms of life quality of these. What I'll be talking about now is I'll be talking more about learning, creativity, innovation. How do we motivate children? How do we motivate ourselves to do these kinds of things with robots? So this is some of my previous work in this area. I've been doing many different things with different robots in various contexts. Originally we started building self-reconfigurable robots. I was Kasper's PhD student, and we were doing these kinds of robots, building different types of modular robots. I visited your lab, worked on the roombots at some point, programmable matter. So we're exploring all these different modularity, self-reconfigurable and self-reconfigurable robots. And lately it has been more about how do we make these systems interact with people, and how do we make them useful for people to do something new. So I have here some examples of Fable, which I brought today, but we have also been developing products with Lego, something I cannot show yet, but like with the Lego Mindstorms team we have been building new products, hopefully coming up in 2017, at least that's the plan. We're working with underwater robots for inspections in the offshore sector, these modular robots that can collaborate and do all kinds of interesting stuff. So different aspects of this. But what this talk is really about is the background for this project is really the educational system is under pressure. So a lot of the courses that the children are being taught in school were kind of made up during the industrial age. And the world has changed since the Industrial Revolution. Now they need to learn new skills. They need to learn to be creative with technology. They need to learn not just to use an iPad, but they need to be able to create with technology, create robots, create iPads, learn to program, understand technology on a different level. So that's the background. And teachers and parents and politicians, they all know this. So they're putting a lot of requirements on the educational institutions in order to kind of integrate technology into the classroom. So, but they have very limited resources to do this. They don't get a big extra budget to integrate this. Furthermore, they need to do inclusion. They need to have also more challenged pupils come into the classroom, and they need to develop all these students' talents for the future. I mean, we don't need so many factories workers anymore. We need people who are creative and bright and so forth. So, and then one very concrete aspect, they need to learn to program, but the teachers have never tried to program themselves. So it's very difficult for them to start to learn children to program when it's something they have not even tried themselves. So our background when coming to design such a system is how do we imagine learning? And we think that learning should not be like this. I mean, learning should not be something where a teacher tries to pour information into the head of his students, because it only creates this kind of scenarios which really sleepy pupils. So what is much more appropriate is this kind of learning spiral where you are actually creating and being a creative part of the process of creating something with your mind and with your hands. So like these children are doing here, they're creating some kind of wooden bird house. So this is the spiral of coming up with a bright idea. It would be really good to build this kind of thing. And then you go and try to create it, and you do some experiments with it, and you show it to your friends, and you say, okay, this is really cool. But then you start to think, maybe I could do something slightly better, maybe I got a new idea. And then you get to imagine something else, and now you're slightly brighter, and you have slightly more experience, and you can gradually cycle out in this spiral to kind of build your own competence, or build your own knowledge, and also build with the tools that you provide. So this is not something I invented. This comes from Seymour Papert, who made this learning theory of constructionism, and he says these kinds of things like learning occurs as the result of the learner's active participation, being active, trying to learn something. And we don't educate learners, we create a context in which they learn. So, setting up a room filled of robots and computers and these kinds of things is an environment for learning, an environment where you can experiment in. You don't get ideas. I mean, ideas are something which is handed from someone to you. It's something you create yourself. I mean, even if you tell me an idea, I have to make it my own before I can really start using it. And finally, knowledge is not something which is required, but it's something you need to construct when you're working with the things. You construct it as mental models. So what he did was very concrete and hands-on. He built this local programming language back in the 80s, and he was teaching young children to program because he saw computers as this fantastic tool that could create these kind of micro-environments that you could learn with. So this is a nice little program with this kind of turtle, and it can do different functions like moving forward, turning right 45 degrees, and moving forward again 25 degrees. So, and then it will draw this small line while doing it. And if you do, for example, this kind of recursive program, well, then you can create, for example, this impressive tree structure. So it's a very visual way for the children to engage in this kind of micro world. Also, Lego Mindstorms came from this lab. So actually, Lego set up this kind of group just on the other side of the river, working very closely together with Ms. Resnick's group in order to create the very first versions of the Lego Mindstorm, and which then came out in the mid-90s. And Lego Mindstorms is also named after the book that Seymour Papert wrote. So there's a very tight correlation between these two things. So. And we really think, Lego Mindstorm is a great tool for learning, but it also has some limitations. And one of the limitations it has is that it takes a lot of effort to build something. You have these hundreds of different components, and it will take you an hour or 2 hours to build a robot. And if it takes you 2 hours to build a robot, you're not going to be very motivated to take it apart and try something new, because you invested a lot of time in this thing. So there's a tendency when learning to use with Lego Mindstorms, you build the thing once. For example, in a classroom setting, you build the robot, and then they will never be changed before the project is over. And usually it will be it'll take them a day to build the robot, or the teacher will do it for them, which is something they don't have enough time to do. So it's a great tool, but it has its limitations. So we built something called the Fable system, which is what we have on the floor here, and which is kind of some CAD models of it here. So it consists of different modules, and you could imagine many more modules than this. This is just kind of our first basic set of modules. Some of these modules are these kind of passive modules. So some of them are just plastic modules with magnetic connectors that you can click together in different ways. And some of them are these actuated modules, which you can turn on, and then you can program them from a computer, make them move, make them do different things. You can combine them in many different ways to create many different types of robots. So what is Fable? So it's a learning tool So we're trying to make something which makes it, which makes the children solve problems, come up with bright ideas and try to solve concrete problems. So through this development of robots, hopefully they will learn a lot about different concrete things like math and physics and other things, but also more general things about how to solve problems, how to split problems into smaller components that can be solved separately, how to design algorithms of these kinds of things. Inclusion is another thing. So, for example, something like this is fairly simple for small children to get started with. While if you build something more like this, a walking robot, it's a more challenging task. So you can have something which is within the same setup, within the same system. You can have something which is appropriate for small children or for unexperienced children, or you can have something which is more appropriate for more experienced children. And finally, it's very fast and easy. So in the Danish school system, most classes are divided into 45 minutes lessons, sometimes 90 minutes lessons. And if you want to set up something that works in 45 minutes, where it needs to be sort of put into the classroom, taken out all to all the children, and then by the end of 45 minutes put back in boxes and put in the chargers and put back, then you really need something that's very fast and very easy for the teachers, otherwise it's just not going to happen. So we try to make it as easy and simple as possible to use. So one of the things which we can do is we can have different levels of complexity when it comes to the programming. So we have something called Broccoli, which is this visual programming language, which I'll show you an example of, which allows like up down to 8-year-old children to program the system. And then when they kind of become too constrained from this, they can move on to more advanced things like Python, which is still very user-friendly, and they can actually start programming things, for example, in high school. Also for ourselves, like we are researchers, we might work in MATLAB or Java or whatever programming language we want, and we can create genetic algorithm or neural networks, and we can make very advanced controllers for these kinds of robots. So in that way you can use it from 8-year-olds all the way up to research projects, as we also do. So here's an example of how this block programming language look like. So there's a small speak function here which allows the robot to say something, then a while true, and then forever it will set a position, it will get the position of module number 11 on I-axis. So for example, these modules here have an I-axis and an X-axis. So we get the position from there, put it into a variable, and then it moves module number 13 to that position. So this is kind of a mirroring application of the robot. So one module is controlling another module, and we also make a small graph of it. And this can be directly translated from this Broccoli code into Python code, kind of creating this type of stepping stone for the children to take one step from this type of programming language, the visual programming language, to the more textual programming language. So here's a video. So this is a small program for remote controlling. So you write your own remote controller. So this is remote controlling this small wheels module. So this is an example of a walking robot. I didn't show the program, it's too big and it's too complicated to really understand in just a few seconds. But it allows you to do exactly the same thing, but now instead of remote controlling just the direction of the movement of the wheels, you're actually controlling the angles of the motors individually to create these kinds of gates. So, as I said, it takes very little time. You have these strong connection mechanisms that are four-way redundant, meaning you can combine them in 4 different ways. They're magnetic, it takes some time to connect. You have this kind of programming interface where you plug in a USB dongle into a PC, and then you can start programming as soon as the robot is coupled with the dongle, which is done through colors. So if you have a red dongle, you should have a red module so that you can control the robot. So here's an example of some assembly of modules. start to create all kinds of weird things. And the point here is that we have not developed all the modules we want to develop yet. We're going to just kind of keep expanding the system with new types of modules to create new kinds of possibilities with the system. But still you can create quite a number of different robots. Here are some examples like walking robots, snake robots. And since this is a wireless controlled system, you can actually create these kinds of swarm robots also and do different interesting things. Here's another little example video, kind of the code that I showed in the beginning, where the actuators here are mirrored by the movement of this actuator here. So what's going on here is this module is sending wirelessly communication back to the PC, which is running this program written in Block, which is then sending out commands to these modules moving this motor. You can also set up the classroom in such a way that the children are not individually or in groups of two, for example, programming a small robot. They can actually work in several groups together, for example, programming a robot, taking turns, sending the program to them, so they can have this kind of collaborative programming, which is also something new. This is a project which started back in 2012, where we started doing this. It looks very similar, but it's actually from the inside it's very, very different. We didn't have integrated electronics properly, and we had this global programming language, so we're actually using the original run from Simon Paper, but it was very difficult for the children to use. So we started integrating things more, putting electronics inside the modules and finding better ways to produce them, so that we are now at this prototype stage here. Then I'll also tell you a little bit about the tests that we are doing. So we're doing different tests in schools with the children programming robots. And we're also doing more research kind of projects where we are letting the children, or we are setting up experiments for exploring different ways to interact with the system. For example, this one here is the interaction is the pitch of the voice. The pitch of the children's voices are controlling different things for the robot. So in one example, for example, they could, by using different tones and the pitch of the voices, they would make the robots do different actions. And we could actually allow them to program their own actions. So when you were saying like a very high pitched sound, like it would move left, for example. So you kind of try to create this kind of playful, but still a very different way of interacting with the robot. Also in this example here, it's more with like a Kinect type camera, where the robot is able to actually detect the girl's movement and mirror them, or maybe create some kind of games where she has to mirror the robot. But most of our experiments are about programming, and I'll show you just one example we did just a couple of weeks ago, which is from a Danish public school. We had all these, we had the full classes of robots, and then we had 375 pupils working with the system in 2 weeks time. So they were from 2nd to 8th grade, and each of them had 4 lessons of 45 minutes with the robot. So we started out with programming lessons where they learned to program the system. Most of them had never programmed before. So they learned different small things like how to make the robot move, what is a while true loop, and what is an if, and these kinds of things. So they spent maybe 45 minutes with this, and then they started building these type of very small projects that we gave them. For example, a throwing robot, combining Lego with our system, we can make it kind of throw a ball. So they could experiment with this and just play around with the system. And in these 2 lessons we were present, so there was always engineers from the Technical University of Denmark there. But then in this 3rd and 4th lesson we actually left, and the teachers were alone with the whole class themselves, trying to come up with various projects that the children would work on. So this was a very, when working with robots, you know, it's very nerve-wracking that usually the robots break down all the time. So getting to a stage where we can actually leave the robots and not be present while it is being used is a big step for us. So this was a very interesting test, and we learned a lot from these experiments. And also we learned a lot about how little time the teachers have, because they really have no time setting up anything. It basically has to be ready in the classroom in 2 minutes, because otherwise they don't get the coffee, and they have very little time between the classes. And the coffee is important, as we all know, since there's no coffee. So this is a 2nd grader. They are building robots. It's just a nice picture. He's smiling, and they are building something. I'm not sure what. This is kind of a typical setup in a classroom. You have maybe 2, sometimes 3 students working together on a single robot with a laptop, and they are solving some kind of exercises that we have given to them in advance. So this is a typical setup. Then later on they start to move on to more advanced things, like C here is trying to make this kind of throwing robot. Easily imagined. So she's and also, I mean, so she's trying to program something, but usually the programs tend to grow and grow in the beginning, so they don't like to delete things they have built. So it just kind of grows and becomes more and more complex for them. But still, at some point, they start to get why things don't work, and they quickly actually pick these things up. Here's another example, another throwing robot. So, and then they start to move on to other things, like combining wheeled things with an arm. And for example, here they have built a nice little car that is supposed to drive and then throw a ball at someone, one of their friends. Here's another nice project where they built something huge, and I was very nervous that it would actually fall into the computer because it's actually very heavy. And this is a torture machine, he told me, so it's easy to imagine how this could torture someone, and it was definitely easy to imagine for him. And this is a boxing robot, so they would be standing like this, boxing, and they would be like putting their head against the robot's arms so they could fight it. And they would then later they put wheels on it, and they would be driving around boxing. And also like the ad hoc football games were very popular. So here is so now they have built a small goal in Lego, and they have built these small remote controllers for the robots. They programmed the remote controllers for the robots, and now they are playing soccer against each other with these robots. Yeah, so that's what I wanted to tell you about education, and then I wanted to take maybe like one step more towards the research project, because we're actually involved in other projects as well. For example, the Human Brain Project. So some of you may have heard of the Human Brain Project. It's this huge flagship project, 1 billion euros, I believe, and hundreds of partners. And within this project, they're trying to create this kind of cluster computer that is able to simulate a big chunk of the human brain. And our role in this is within something called the Neu Robotics platform, where we are looking at self-adaptation in modular robots. So what we're actually doing is we're taking the brain simulations that other partners are creating in the project, and then we are coupling them with robots in the Fable robot, for example, and also the Neu Robotics from Technical University of Munich. So we're closing the loop between this simulation and the hardware in order to understand, in order for the neuroscientists to understand whether or not what they are doing is correct. So it's a way for them to validate if the brain models they are actually building makes any sense at all, because if they're able to actually control a physical system, then at least it makes some sense. Otherwise you have very little way of figuring out whether or not whether or not the brain models are useful for anything. So that's a nice kind of backstory. We're also doing other research projects, but this is one of our most active ones. So that was more or less what I wanted to tell you. So what we are currently doing is we are building more module types, we are fine-tuning the system, we are making education materials for the teachers, and we are trying to make a smart device app so we can program the system from a tablet and this kind of things. And then we're trying to bring the system to market. This involves a lot of redesign of the system because you need to mass produce it, which is something you need to do in a very different way. And then already from the spring we are planning to start to sell to the Danish schools, and we have created a spin-out company which is supposed to do this task. So that's what I wanted to tell you, and you're welcome to come and try and program the system and play with it yourself, just like the Danish Minister of Research and Education did just a few weeks ago at the World Robotics Olympics. So that's it for me.